Europe's most ruthless budget airline found a way to pocket millions without buying new jets or slashing staff. The secret? A strangely curved upgrade bolted onto its Boeing 737 wings that claims just a modest 1 to 2% fuel savings. But scaled across 400 aircraft and thousands of flights, that upgrade would change RyanAir's bottom line forever. How does an almost invisible slice of engineering deliver outsized profits? And what hidden forces are at work every time a plane takes off? Every time a plane takes off, something invisible but powerful forms at the tip of each wing. High-pressure air from beneath the wing spills over to the low-pressure air above, curling around the tip and spiraling away as a vortex. These swirling trails, though unseen, act like invisible anchors, dragging the aircraft back and forcing the engines to work harder. In aviation, this penalty is called induced drag. Unlike the friction that comes from air brushing along the fuselage, known as parasite drag, induced drag is a direct consequence of generating lift. The stronger the lift, the stronger the vortex, and the greater the drag. NASA's research describes this effect as a tax on every kilogram of lift produced. For a typical jet like the Boeing 737-800, induced drag can make up as much as 40% of total drag during takeoff and climb, and remain significant at cruising speed. The problem is baked into the shape of the wing itself. A flat board slicing through air always leaves behind a swirling wake at its edges. The energy lost into these vortices is energy that could have been used to push the plane forward. Over thousands of flights, even a small amount of extra drag multiplies into a mountain of wasted fuel. Imagine riding a bicycle with a flag flapping behind you. That fluttering flag isn't just decoration, it's pulling you back, making you pedal harder. On an airplane, the wingtip vortex is that flag, except it is made of air, and there is no way to take it off. Engineers have spent decades searching for ways to tame these invisible spirals and reclaim the energy lost to induced drag. Aviation partners, Boeing set out to tackle induced drag with a radical hardware rethink. Their answer was the split scimitar winglet, a device that reimagines the tip of the Boeing 737-800's wing as a three-part aerodynamic tool. At first glance, it looks like a sculpted blade rising from the wing, but the real engineering is in the details. The main element sweeps upward in a graceful arc, the upper blade channeling airflow away from the tip. Beneath, a sharply angled extension shaped like a downward-pointing sword slices the air below. This lower scimitar, paired with a ventral strake, splits the vortex into weaker streams, disrupting the spiral that would otherwise sap energy from the wing. Aviation partners. Boeing, APB, first commercialized blended winglets in the early 2000s, but by 2010, their engineers saw room for improvement. Computational fluid dynamics and wind tunnel tests revealed that the classic upward blade, while effective, left some residual vortex energy untapped. By adding the split geometry, an upper and lower scimitar plus the ventral strake, APB raised the span efficiency factor, bringing the lift distribution closer to the elliptical ideal that minimizes drag. The new design added only a few hundred kilograms to the aircraft, but promised outsized returns. A PB claims the split scimitar configuration can cut fuel burn by as much as 5.5% compared to a bare wing and 2% over the earlier blended design. Airlines like Qantas and United Airlines validated these numbers in field trials, reporting thousands of gallons saved per aircraft each year. By 2017, nearly 900 aircraft had been fitted with the split scimitar kit, and APB's data showed a cumulative savings of 7 billion gallons of jet fuel worldwide. The technology was ready for any airline seeking a proven, off-the-shelf solution to a decades-old aerodynamic problem. RyanAir's finance team, led by the chief financial officer and the head of fleet management, faced a familiar challenge: how to squeeze more efficiency from a fleet already running at full tilt. In 2013, with jet fuel making up nearly a third of operating costs, the airline's internal working group assembled a cost-benefit matrix to weigh every possible path to lower fuel burn. Buying new aircraft like the 737 MAX promised major savings, but required huge capital and long delivery timelines, and was out of sync with RyanAir's need for rapid returns. Cabin weight reduction programs offered only modest gains, and the certification costs threatened to swallow much of the benefit. The retrofit option stood out. For a fraction of the price of a new jet, the split scimitar winglet kit could be installed on existing 737-800s with no disruption to the high-frequency schedule. The forecasted 1 to 2% cut in fuel consumption, when multiplied across thousands of flight hours per plane, translated into millions of euros saved each year. Internal models showed a payback within just 2 to 3 years, even with conservative fuel price assumptions. The board saw the numbers and did not hesitate. Approval was unanimous. By September, RyanAir had signed a contract with aviation partners Boeing, locking in a performance guarantee and setting the stage for a fleet-wide transformation. The decision reflected RyanAir's core strategy: pursue upgrades with low upfront cost, short payback, and a clear, measurable impact on the bottom line. With the green light given, the focus turned to the regulatory maze that would determine how quickly the new winglets could start paying dividends. Approval from regulators was the first real hurdle. Because the split scimitar winglet retrofit changes the aerodynamics of the Boeing 737-800, RyanAir could not simply bolt on the new kit and put the aircraft back in service. Aviation partners Boeing submitted a supplemental type certificate package to the European Aviation Safety Agency, detailing structural analyses, flight test results, and wind tunnel data. ESA issued the official STC in January 2014, laying out strict conditions. Every winglet installation required a visual and torque inspection every 12 months, and each aircraft needed updated weight and balance documentation to reflect an increase of 200 kilograms from the new hardware. The Irish Aviation Authority, responsible for RyanAir fleet, signed off on the same terms. With the paperwork cleared, RyanAir maintenance team launched what they called the Scimitar Sprint. 3 main maintenance hubs, Dublin, Warsaw, and Alicante, were assigned to handle the retrofit. Each hub operated multiple bays, with teams working in parallel to minimize downtime. The process was a study in efficiency. Aircraft were withdrawn from service, parked in dedicated zones, and stripped of their old wingtip devices. Technicians installed reinforcement plates at the wing root, then attached the new split scimitar assemblies using alignment jigs and torque wrenches. Wiring for the anti-ice system and a quick software update rounded out the job. Every step was checked, logged, and signed off before the plane returned to the schedule, often within a single day. To keep the operation running smoothly, RyanAir sent its maintenance and engineering crews through a 3-day training course with aviation partners Boeing instructors in Toulouse. The curriculum covered aerodynamic theory, load path verification, and troubleshooting for the new anti-ice system. By the end of the rollout, nearly 200 aircraft had been retrofitted in less than 2 years without disrupting RyanAir high-frequency timetable. The real test, though, would come in the numbers: how much fuel the new winglets actually saved once the fleet was back in the air. Independent assessment was essential to confirm that the aerodynamic upgrade delivered real savings outside the test lab. In 2020, a team from the University of Southampton's Aeronautics Department received access to RyanAir's flight data recorder logs covering thousands of flights before and after the retrofit. Their statistical analysis found an average fuel burn reduction of 1.4% across the retrofitted fleet, with a confidence interval from 1.1 to 1.7%. The benefit was most pronounced on longer routes over 1,200 kilometers, where the cruise phase accounts for a larger share of total flight time, approaching a 1.9% reduction on those sectors. Shorter hops saw more modest improvements, around 0.8%, reflecting the smaller role of cruise drag. The numbers add up quickly at scale. By the end of 2022, RyanAir reported a cumulative saving of 30 million liters of jet fuel, verified by external auditors under the European Union emissions trading system, using the ICAO standard conversion factor that translates into 95,000 tons of carbon dioxide avoided. No independent study has contradicted these figures. Even the most skeptical industry analysts concede that the retrofit's aggregate impact is real, if slightly less dramatic on ultra-short flights. The evidence leaves little doubt the split scimitar winglets delivered measurable, fleet-wide efficiency gains, verified both by academic researchers and regulatory audits. Each retrofit came with a price tag of around €235,000 per aircraft, covering both the hardware and installation. For RyanAir's 197 jet fleet, the total bill landed just above €46 million. But the real calculation started once the planes were back in the air. With every hour flown, the split scimitar winglets trimmed fuel use, translating to an average annual saving of €78,000 per aircraft. Multiplied across the fleet, that is more than €15 million saved on fuel each year, enough to pay back the entire investment in just 2.6 years. Even when fuel prices dipped, the numbers held up. At low market rates, the payback stretched to just under 4 years, while at higher prices the return arrived in less than 2 years. RyanAir's finance team ran the sensitivity tables and found no scenario where the retrofit failed to deliver a positive return. The performance guarantee clause from aviation partners Boeing added a final layer of security, promising a refund if the savings ever fell short of expectations. In the unforgiving world of airline margins, the math was unambiguous. A modest modification, repeated at scale, produced a compounding financial advantage that few other upgrades could match. A single design tweak measured in centimeters now saves RyanAir over 65,000 tons of jet fuel each year. As fuel prices and emissions targets tighten worldwide, every fraction of efficiency counts. In aviation, the smallest upgrades can redefine the bottom line and the future of flight. What would you upgrade next?